847 earthquakes, 30 days. That is 70 times the normal seismic frequency for the Philippines. And every single one of those tremors is feeding energy directly into a fault system that scientists say is already past due for the most destructive rupture in the country's recorded history. The West Valley Fault runs for 100 kilometers straight through the core of Metro Manila. Not around it. Not beneath its outskirts, through its center, under the financial towers of Makati, under the crowded residential streets of Quezon City, under the schools and hospitals and underground rail lines that 13 million people depend on every single day. This fault has not produced a major rupture since 1658. That is 368 years of uninterrupted tectonic pressure, compressing deeper and harder with every passing decade, with no release and no relief. Scientists are not divided on what happens next. PHIVOLCS Director Renato Solidum has stated it plainly. The West Valley Fault will move. The only variable that remains unknown is the specific moment it finally does. But something is different right now. Something that has seismologists studying their monitoring data with a level of concern that goes far beyond routine scientific caution. These 847 earthquakes are not random. They are not a collection of isolated tremors scattered by chance across a wide map. The data shows a mechanical sequence, a synchronized transfer of energy moving fault by fault, region by region, converging on a single destination. And that destination is the ground beneath 13 million people. When the West Valley Fault finally ruptures, PHIVOLCS projects 90 seconds of intense shaking across the entire metropolitan corridor. In those 90 seconds, models indicate that more than 170,000 buildings will sustain damage severe enough to collapse or render them uninhabitable. GCA casualty projections estimate over 34,000 deaths from the initial shaking alone. More than 1 million residents will lose their homes in under 2 minutes. And the brutal physical reality that compounds all of it is that no alert system on Earth moves faster than the seismic waves that will already be tearing through the city before any warning can reach a single person. So the question that every seismologist studying this system is now asking aloud is this: has the 2025 earthquake swarm crossed the threshold that finally triggers the rupture? And does Metro Manila have any time left at all? To understand the scale of the threat, trace the West Valley Fault from start to finish. It originates in Bulacan province in the north, cuts southward through Quezon City, threads directly under the high-rise financial corridors of Makati, continues through Pasig, Marikina, and Muntinlupa, and finally terminates in the provinces of Cavite and Laguna to the south. Every major urban center in Metro Manila falls along this path. Every densely packed neighborhood, every school building filled with children, every hospital operating around the clock, every office tower anchored into the earth above this geological fracture. More than 13 million people occupy the immediate rupture zone, and virtually none of them have a viable way out once the ground begins to move. The historical record deepens the alarm. The West Valley Fault does not release pressure frequently. Scientists have identified its rupture cycle at somewhere between 400 and 600 years, meaning its energy accumulates over centuries before a single catastrophic release clears the system. The last confirmed rupture occurred in 1658, that is 368 years ago. By every geological measurement currently available, this fault is not approaching the outer edge of its rupture window. It has already moved past it. The stored tectonic energy does not diminish while the fault waits. It grows. Each year without rupture is another year of pressure locked into a system that scientists agree has already exceeded its historical threshold. PHIVOLCS projects that when the rupture occurs, the earthquake will register at magnitude 7, 2 or greater. Ground shaking will persist for between 60 and 90 seconds. Surface displacement along the fault could reach 4 meters in the most severely affected zones. The forces generated will exceed the structural design tolerances of the vast majority of buildings currently standing above the rupture corridor. Every model, every projection, every scientific analysis of this system points toward the same outcome. The question that remains is only the calendar date attached to it. The Philippines does not simply experience earthquakes. It is built on the intersection where more tectonic forces collide than anywhere else on the planet. 4 massive plates converge directly beneath the 7,641 islands of the Philippine archipelago simultaneously. The Philippine Sea Plate drives westward beneath the islands with enormous force. The Pacific Plate pushes in the opposing direction. The Eurasian Plate exerts pressure from the north. The Sunda Plate pushes upward from the south. 4 geological masses, each one incomprehensibly large, all converging at the same coordinates, all transferring stress into the same interconnected fault network at the same time. Consider the comparison. Japan, one of the most seismically active nations on Earth, manages interactions between 2 tectonic plates. California, globally recognized as a high-risk earthquake zone, sits along a 2-plate boundary. The Philippines deals with 4 converging simultaneously. That is not simply twice the danger. The complexity multiplies tectonic stress in every direction at once, creating a geological pressure system where energy accumulates from all sides with no avenue for gradual release. For generations, this configuration produced a rhythm that scientists could at least study and anticipate. The Philippines typically recorded roughly 100 measurable earthquakes annually. Approximately 20 caused meaningful damage. Tremors occurred with enough regularity that they represented a dangerous but somewhat predictable background condition. The country built its infrastructure, its emergency systems, and its scientific monitoring programs around an understanding of that baseline. That baseline no longer exists. In the span of 30 days, 847 earthquakes have struck the Philippines. The normal monthly range sits between 8 and 12. Microseismic activity has more than doubled compared to equivalent periods in prior years. The predictable rhythm that held for generations has fractured. And what has replaced it is something that seismologists describe as genuinely unprecedented in the documented scientific record of this region. The reason this collapse of normal patterns carries such specific danger relates directly to how the Philippine fault network actually operates. The West Valley Fault does not function in isolation. Neither does the East Valley Fault, the Philippine Fault Zone, or the Manila Trench. These systems are mechanically linked through a process of stress redistribution that runs beneath the entire archipelago like a pressurized underground circuit. Dr. Deo Carlo Bringas of PHIVOLCS has described the dynamic as a pulse moving through the entire island chain. Each earthquake releases tension at its point of origin, but simultaneously redirects stress outward to every connected fault system surrounding it. The pressure does not dissipate, it migrates. And right now, it is migrating faster and across a wider geographic range than any prior monitoring period has ever recorded. September 2025 delivered the opening shock, a magnitude 6. 9 earthquakes struck Cebu with devastating intensity. At least 79 people died. Buildings throughout the Visayas region collapsed. Emergency response teams worked through rubble searching for survivors, while families in communities across the island processed catastrophic loss. The disaster was severe by any historical measure, but what followed changed the entire scientific picture. 10 days later, a magnitude 7. 4. Earthquakes struck Mindanao with ferocious force. Ground shaking lasted nearly a full minute. Communities that endured the initial rupture immediately began search and rescue operations under conditions of extreme stress. Then, within hours, a magnitude 6. 9. Aftershock struck from the same fault zone in rapid succession. Scientists classify this as a doublet earthquake, 2 major events from a shared source with minimal separation in time. The phenomenon is rare. When it occurs, the stress redistribution effects across neighboring fault systems are amplified dramatically. 10 additional people died, over 1,000 sustained injuries. Communities that had survived the first blow had no recovery window before the second arrived. Then came the figure that reframed everything: 847 earthquakes in 30 days, against a normal monthly baseline of 8 to 12. That is not a modest statistical deviation. That is not a number that fits within any model of normal variance. That is a 70-fold acceleration of seismic activity unfolding right now beneath one of the most densely populated nations on Earth. The numbers are not leveling off. They continue to rise. But the raw count is not the most alarming element. What PHIVOLCS analysis has identified within this data is something that researchers describe as structurally unprecedented. The swarm is not a collection of independent seismic events occurring in parallel. It is a synchronized mechanical sequence, with each earthquake transferring measurable stress to neighboring fault systems in a pattern that builds progressively toward a single geographic endpoint. Dr. Deo Carlo Bringas has explained the chain with precision. Each tremor releases tension at its source location while simultaneously loading pressure onto every connected fault system in the surrounding region. Stress from Mindanao propagates northward toward the Visayas. Energy from Cebu transfers upward toward Luzon. Each successive tremor in the swarm pushes cumulative pressure closer to Metro Manila. And the West Valley Fault absorbs all of it, sitting 368 years past its established rupture threshold, receiving additional stress from every earthquake that strikes anywhere in the archipelago. Most people carry a mental model of earthquakes as localized events. The ground shakes at the fault, the energy dissipates nearby, the crisis remains geographically contained. The model is fundamentally incorrect, and the gap between that assumption and scientific reality carries catastrophic implications for 13 million people. When an earthquake occurs, the energy it releases does not vanish beneath the epicenter. It propagates outward through the Earth's crust at 8 kilometers per second, physically altering the stress conditions on every fault system it reaches. Scientists call this Coulomb stress transfer. It is not a theoretical concept or a modeling projection. It is a documented physical process with a decades-long evidentiary record. The 1992 Landers earthquake in California triggered measurable seismic responses across multiple states hundreds of miles from the rupture zone. The 2004 Sumatra earthquake redistributed stress across fault systems throughout the Pacific Basin. The 2012 Indian Ocean earthquake at magnitude 8. 6 generated stress transfer effects that reached fault networks in Japan. Each case followed the same mechanical logic. Energy released at one point loads pressure onto the next fault in the connected chain. What distinguishes 2025 is the velocity and the geographic scope. Stress transfer events documented in historical cases typically propagated across fault networks over periods of days to weeks. The patterns emerging from current Philippine monitoring data are occurring in minutes to hours. 7 major fault systems are responding in apparent coordination to ongoing seismic activity across the archipelago. Coordinated multi-fault seismic response at this speed and over this spatial range has no documented parallel in the scientific record. Dr. Ross Stein of the United States Geological Survey has characterized what is unfolding with directness. What the current data from the Philippines represents is earthquake clustering operating at an international scale. The archipelago is not generating contained regional seismic events. It is functioning as a mechanical transmitter, sending pressure outward through a fault network that spans the entire Western Pacific. And the energy moving through that network has a measurable trajectory. Mindanao earthquakes load stress northward onto Luzon fault systems. Visayas aftershocks push energy upward through the crust toward the capital. The Manila Trench registers elevated pressure accumulation along its full extent. Philippine sea plate boundary activity reflects a seismic background state that scientists characterize as deeply abnormal. Every component of this system is pointing toward the same location. The West Valley Fault sits at the terminal point of this cascading pressure transfer. It absorbs stress from every tremor generated anywhere across the archipelago. It adds each new increment to a 368-year accumulation that already exceeds every historical threshold scientists have identified for this system. The stress transfer process is not a working hypothesis. It is measurable. It is accelerating. And every seismic event recorded in this swarm is another data point confirming the direction of travel. When the West Valley Fault ruptures, the initial 90 seconds will determine the survival outcome for millions of people before any emergency response system can deploy a single resource. Ground acceleration in those 90 seconds will exceed the structural design parameters of most buildings standing in Metro Manila today. The collapse sequence will not build gradually. It will arrive in full force from the first second of motion. PHIVOLCS and the Metro Manila Development Authority have modeled this rupture scenario with extensive detail. The projections are consistent and severe. More than 170,000 buildings will sustain damage ranging from severe structural compromise to total collapse during the initial shaking phase alone. High-rise towers in Makati and Bonifacio Global City face collapse risks from seismic loading that their engineering specifications were never designed to absorb. Informal settlements housing millions of Metro Manila's most economically vulnerable residents offer essentially no seismic resistance. Structures built before modern building codes existed, on compressed lots, without engineered foundations, will not withstand the forces the fault will generate. They will fail within seconds. Liquefaction will follow. Reclaimed land in low-lying districts across the metro will undergo rapid soil destabilization, transforming from apparently solid ground into shifting material incapable of supporting the structures above it. The ground itself becomes structurally unreliable. Schools, hospitals, and government coordination centers all occupy the rupture zone simultaneously and will face identical forces at the identical moment. Infrastructure collapse proceeds in a cascade that severs the city's ability to function. Bridges and elevated road sections fail, eliminating the evacuation corridors that millions of residents would need to move through. The MRT and LRT systems sustain catastrophic structural damage, trapping commuters across the network. Water mains fracture simultaneously across the metro, flooding streets while cutting off clean water supply to everyone who survives the initial shaking. Ruptured gas lines ignite fires that spread through neighborhoods already buried under debris. The power grid fails across the entire capital region, leaving 13 million people in complete darkness in the first moments of a disaster that demands visibility to survive. JICA's detailed casualty modeling for this exact scenario produces numbers that are difficult to process. More than 34,000 people dead from the initial shaking alone. Injuries exceeding 100,000. Over 1 million residents displaced from homes that the rupture will have erased. The death toll does not stop when the ground stops moving. Secondary mortality from uncontrolled fires, waterborne illness in the absence of clean supply, and the collapse of medical infrastructure continues accumulating for weeks as the city attempts to function without power, potable water, or passable roads. Metro Manila contributes 36% of the entire Philippine national economy. When the business districts fall, the economic damage extends across the country and outward into regional trade networks. Recovery timelines, by expert consensus, are not measured in months, they are measured in decades. In 90 seconds, the West Valley Fault will not merely damage a city, it will restructure the Philippine nation, and multiple generations will spend their lives rebuilding what those 90 seconds consumed. PHIVOLCS operates one of the most technically advanced seismic monitoring networks in the Asia-Pacific region. Monitoring stations are distributed across the archipelago, tracking ground motion continuously around the clock. Detection systems identify earthquakes within minutes of occurrence. New stations have been positioned specifically throughout Metro Manila. Scientists maintain 24-hour active surveillance of the full 100-kilometer West Valley Fault rupture zone. The scientific commitment is genuine. The technology is current. The expertise is real. And none of it changes what happens when the fault breaks. The physics make the outcome unavoidable. Seismic waves travel through the Earth's crust at 8 kilometers per second. No human-engineered system processes and transmits information at anywhere near that speed. Seismic detection equipment requires a minimum of 2 to 3 minutes to analyze initial earthquake data. Tsunami modeling systems need 5 to 10 minutes to calculate projected wave arrival times. Coordinating alerts across international borders takes 10 to 15 minutes. Issuing a formal public evacuation order through official channels takes 15 to 30 minutes at minimum under ideal conditions. For a fault running directly beneath a city, every one of those timelines is irrelevant. The destruction begins before the first alert can be transmitted. The shaking arrives before anyone can be instructed to move. By the time any warning system could theoretically reach 13 million people, the initial collapse sequence will already be complete. 4 structural failures in the existing warning infrastructure compound this physical limitation. Fault monitoring across the region operates on a nation-by-nation basis with minimal real-time data sharing across borders. Tsunami simulations are built around single fault rupture scenarios rather than the kind of cascading multi-fault sequence that 2025 data now suggests is increasingly possible. Communication delays between national agencies make coordinated multi-country alerts functionally impossible to execute within any operationally useful time frame. And existing data processing systems were engineered for normal seismic input volumes, not for simultaneous high-frequency data streams flooding in from multiple active fault systems at once. Manila Bay faces exposure to tsunami-generating events along the Manila Trench. If multiple fault systems rupture in a connected sequence, their resulting tsunamis could interact through wave superposition, layering on top of one another and producing amplified inundation heights that no current model has been designed to calculate. No existing warning protocol was developed with that scenario in scope. Dr. Katsuichiro Goda of the University of Bristol has been unambiguous about what this gap means in practical terms. Cascading seismic hazards now represent a distinct category of disaster that existing monitoring and warning infrastructure is fundamentally unprepared to manage. Warning system architecture needs comprehensive redesign to account for the realities of stress transfer in interconnected fault networks. The systems currently in place were built for a previous understanding of seismic risk. The threat has outpaced the technology designed to address it. And 13 million people are living inside the interval between those two realities. PHIVOLCS continues doing everything that current science enables. Continuous 24-hour monitoring of the full rupture zone. New sensor deployments across Metro Manila. Real-time stress accumulation tracking. Public preparedness campaigns raising awareness about the fault's inevitability. Every earthquake in the current swarm deposits additional stress. Every day that passes compresses the timeline further. The fault does not accommodate delay. The West Valley Fault will rupture. PHIVOLCS has stated it. JICA's models are built on it. Every seismologist who has studied the system in depth has reached the same conclusion. This is not alarmist framing designed to generate attention. It is geological reality validated by centuries of seismic data, confirmed by decades of field research, and supported by the unanimous scientific consensus of every credible researcher who is engaged with this fault system. The rupture has happened before. It will happen again. The only genuine unknown is the specific moment when 368 years of accumulated tectonic stress finally exceeds the capacity of the rock above it to hold. The 2025 earthquake swarm has changed the terms of this conversation in a fundamental way. What scientific literature once described as a severe but temporally distant inevitability has transformed into a measurable, accelerating, data-confirmed threat unfolding in real time. In 30 days, 847 earthquakes have struck the Philippines, 70 times the normal monthly frequency. Each tremor loads additional stress onto fault systems already compressed beyond every historical marker scientists have established. The magnitude 7, 4, Mindanao earthquake. The magnitude 6, 9, Cebu disaster that killed 79 people. The doublet strike that left over 1,000 injured. These events are not random seismic noise scattered across a wide geographic field. They are a sequence. A directed, mechanically connected progression of pressure transfer moving toward a single point. The final point in that chain is the West Valley Fault, sitting directly beneath Metro Manila, absorbing cumulative stress from every tremor generated anywhere across the archipelago, growing more critically loaded with each passing day. The science of Coulomb stress transfer has eliminated any residual ambiguity about this connection. Earthquakes do not honor provincial boundaries or national borders. Energy released in Mindanao travels northward through the crust at 8 kilometers per second. Pressure from the Visayas propagates toward Luzon. The West Valley Fault collects the cumulative output of every seismic event across the entire island chain, positioned at the endpoint of a cascading mechanical network that is accelerating in both frequency and intensity with each week that passes. The implications extend beyond the Philippines. Scientists now recognize that fault systems throughout the Western Pacific are mechanically integrated in ways that previous generations of researchers did not fully account for. A significant earthquake in one country can alter the stress conditions on fault systems in another within minutes. The model of seismic events as geographically isolated occurrences no longer reflects the data. What 2025 has revealed is a connected, reactive geological network operating across a spatial and temporal scale that no existing government agency, international institution, or warning system was designed to manage. For the 13 million people living above the West Valley Fault, this science is not abstract. It is the calculation running silently behind ordinary life. The thought a parent carries on the morning school run, the awareness a worker brings into a high-rise lobby every morning, the quiet knowledge that never fully leaves a family in an informal settlement that offers nothing between them and the fault beneath their floor. When the West Valley Fault finally moves, when 13 million people face 90 seconds of structural collapse with no advance warning, how many of them will have done the one thing that science says actually changes the outcome? Prepared before the moment arrived. Because the ground beneath Metro Manila is not asking whether anyone is ready. It is simply deciding when.